Have you ever looked at the night sky, identified a distant planet or star, and thought that the most logical way to get there would be to simply point the spacecraft in that direction and fire the engines? It is a completely natural intuition, built on decades of experience with vehicles that move on flat surfaces or in Earth's atmosphere, where going from point A to point B in a straight line is generally the shortest and most efficient route. But space is not a flat surface. It is not even an empty and uniform space in the sense that everyday intuition imagines. It is a three-dimensional gravitational field of extraordinary complexity, where every planet, every moon, every star, and every massive body in the solar system is continuously pulling on any object moving through it, and where the trajectory that seems most direct visually is almost always the most expensive in terms of fuel, the slowest in terms of time, or simply impossible to execute with the available propulsion. Understanding why spacecraft do not fly in straight lines requires completely abandoning the intuitive physics built on terrestrial experience and adopting a way of thinking about motion that was formulated by Isaac Newton more than 3 centuries ago, and that remains the foundation of all modern orbital mechanics. The first concept that must be understood to grasp spacecraft trajectories is that, in space, under the influence of gravity, the natural state of motion is not the straight line. It is the orbit. When an object is said to be in orbit, what is being said in physical terms is that the object is continuously falling toward the massive body that is gravitationally attracting it, but it is doing so with such a large horizontal velocity that the curvature of its falling trajectory matches the curvature of the surface of the body it is falling toward, so that it never actually impacts. Orbit is not a state of levitation or of weightlessness. It is a state of perpetual free fall in which the direction of the fall always points toward the center of the planet or massive body, while the horizontal velocity keeps the object constantly jumping over the planet's horizon. This understanding is fundamental because it implies that any spacecraft that is not actively using its engines is following a trajectory that is completely determined by the gravity of nearby bodies. And that trajectory is never a straight line except in the theoretical case of an object moving directly away from the gravitational center along the radius connecting them. The second fundamental understanding is that of orbital energy, which is the parameter that determines what orbit an object follows in the gravitational field of a massive body. The orbital energy of a spacecraft is the sum of its kinetic energy, which depends on its velocity, and its gravitational potential energy, which depends on its distance from the massive body. In the absence of propulsion, this total orbital energy is conserved, which means that if a spacecraft rises to a greater altitude and its potential energy increases, its kinetic energy must decrease, and therefore its velocity must fall. And if it descends to a lower altitude, its potential energy decreases and its velocity must increase. This relationship between altitude and velocity is completely contrary to the intuition built on terrestrial experience with conventional vehicles, where going higher simply requires burning more fuel. In space, a spacecraft that has performed an engine burn to increase its orbital energy rises to a higher orbit, and in that higher orbit it moves more slowly than in the lower orbit from which it departed. To go faster in terms of absolute velocity, you have to descend to a lower orbit. To reach a destination sooner that is in a higher orbit, you have to go to an even higher orbit first, one that at some point intersects with the destination orbit, and that requires an engine burn that adds energy to the system. The Hohmann transfer is the most elegant and most studied example of how mission engineers exploit these relationships to move a spacecraft from one orbit to another using the minimum possible amount of fuel. A Hohmann transfer between two coplanar circular orbits consists of two engine burns. The first burn accelerates the spacecraft in its initial orbit, increasing its orbital energy and placing it in an elliptical orbit whose closest point to the planet, the perigee, coincides with the initial orbit and whose farthest point, the apogee, coincides with the destination orbit. The spacecraft then travels along this transfer ellipse without using engines until it reaches apogee, which is the point on the trajectory closest to the destination orbit. At that point, the second burn is performed, which again accelerates the spacecraft to circularize its orbit at the destination altitude. The result is that the spacecraft has moved from the initial orbit to the destination orbit using exactly two engine burns at the precise moments where the Oberth effect guarantees that each burn produces the maximum change in orbital energy per kilogram of fuel consumed. The resulting trajectory looks nothing like a straight line between the 2 points. It is a semi-ellipse that appears to take an enormous detour compared to the direct distance, but that in terms of required fuel is the optimal solution to the orbital transfer problem. Launch windows are a direct consequence of orbital geometry that most people who have not studied orbital mechanics have never considered. For a spacecraft to reach its destination, it is not enough for the spacecraft to be in the correct orbit. It has to be at the correct point in that orbit at the correct moment. If the destination is the moon, for example, the spacecraft has to arrive at the point where the lunar orbit crosses at the same moment the moon is at that point, not 3 days before or 3 days after. This means the launch has to be performed in a very specific time window that can be a few hours or even minutes, determined by the relative positions of the Earth, the Moon, and the Sun at the moment of launch. If that window is missed, you have to wait for the geometry of the system to become favorable again, which for a trip to the Moon can be a month, and for a trip to Mars can be 2 years, which is the synodic period between Earth and Mars, the time it takes for Mars to return to the same relative position with respect to Earth. This dependence on launch windows is one of the most concrete manifestations that space is not a static medium through which you can navigate in a straight line at any time. Gravity assist trajectories, also known as slingshot maneuvers, are perhaps the most dramatic example of how spacecraft exploit the geometry of the gravitational field rather than fighting it. When a spacecraft approaches a planet, the planet's gravity accelerates it as it approaches and decelerates it as it moves away. So that if the spacecraft simply passes by the planet without any engine burn, it exits with the same velocity relative to the planet with which it entered, merely deflected in its trajectory. Up to this point, it seems like a zero-sum game. But the planet is not static in space. It is in orbit around the Sun at a velocity of several kilometers per second. If the spacecraft approaches the planet in such a way that the gravitational deflection occurs in the direction of the planet's orbital motion, the spacecraft exits the maneuver with a velocity relative to the Sun that is greater than the velocity with which it entered. It has borrowed linear momentum from the planet, which loses an infinitesimally small amount of orbital velocity due to the conservation of momentum, but which for practical purposes is completely negligible. Voyager 1, launched in 1977, used gravitational assists from Jupiter and Saturn to reach solar system escape velocity, something that would have been impossible with the chemical propulsion available at the time if the spacecraft had had to fly in a straight line from Earth toward the edge of the solar system, burning fuel the entire way. Orbital perturbations are another phenomenon that makes real space trajectories far more complex than any trajectory calculated with a simplified two-body model. In the real world, a spacecraft in interplanetary space is not influenced solely by the gravity of the Sun. It is simultaneously influenced by the gravity of all the planets in the solar system, with intensities that depend on their mass and their distance from the spacecraft at every instant. The gravity of Jupiter, which is the most massive planet in the solar system, can produce significant perturbations in the trajectories of spacecraft that pass relatively far from it. Solar radiation pressure, which is the force that sunlight exerts on the spacecraft's surface, acts as a small but continuous, constant force that over months or years of flight can accumulate a significant effect on the trajectory. The solar wind, which is a flow of charged particles emitted by the sun, also exerts a force on the spacecraft that has to be modeled and corrected. And for spacecraft operating near Earth, the not perfectly spherical shape of the Earth, whose polar flattening creates an asymmetric mass distribution, introduces perturbations in low orbits that cause the orbital plane of a satellite to precess slowly around the terrestrial polar axis, an effect that satellite operators have to compensate with periodic orbital maintenance burns. Precision navigation in deep space requires techniques that go far beyond the inertial guidance systems that are sufficient for most terrestrial vehicles. A spacecraft on its way to Mars, hundreds of millions of kilometers from Earth, needs to know its position and velocity with a precision of meters per second in velocity and kilometers in position to be able to execute the orbital insertion burn at Mars with the precision needed to enter the correct orbit. Achieving this navigation precision requires radio frequency measurements between the spacecraft and the ground tracking stations of the Deep Space Network, which measure the transit time of radio signals to determine distance, and the Doppler effect on the frequency of signals to determine the spacecraft's radial velocity with extraordinary precision. These measurements, combined with detailed gravitational models of the solar system that include the perturbing effects of all the planets and significant minor bodies, allow calculating the spacecraft's actual trajectory with sufficient precision to plan the necessary trajectory corrections and execute them at the correct moments with the correct amount of fuel. Mid-flight trajectory corrections are another manifestation that spacecraft do not fly in straight lines or follow perfectly predefined trajectories. Imprecisions in the launch burn, gravitational perturbations not perfectly modeled, and navigation errors accumulated throughout the flight require spacecraft to perform periodic trajectory corrections, called trajectory correction maneuvers, or TCMs, which consist of small but precise engine burns intended to adjust the trajectory so that the spacecraft arrives at the destination with the required precision. Planning these corrections is an optimization problem that ground navigation teams solve continuously throughout the entire mission, balancing the precision of the achieved adjustment against the fuel consumed and reserving enough fuel for the most critical maneuvers that occur at the end of the mission, such as orbital insertion at the destination planet. The problem of long-range crewed travel adds an additional dimension to all these orbital considerations. The limitation of consumable resources aboard the spacecraft, especially the time of exposure to cosmic radiation and solar radiation, which are the most serious limiting factor for crew health on a trip to Mars or beyond. A Hohmann transfer between Earth and Mars under favorable conditions takes approximately 9 months in each direction, implying a total radiation exposure that is at the limit of what is acceptable with currently available radiation protection technology. Alternative trajectories that reduce travel time require much more fuel because they involve longer engine burns that add energy to the trajectory beyond the minimum of the Hohmann transfer. The trade-off between travel time, required fuel, and crew radiation exposure is one of the most complex mission design problems that the crewed space exploration community has to solve to make a human trip to Mars viable within a reasonable budget. What all these considerations reveal when examined together is that the way spacecraft move through the solar system has almost nothing in common with the way terrestrial vehicles move from one point to another. There are no roads or direct routes. There is no possibility of simply turning the wheel to correct course without consequences in terms of fuel. There is no freedom to accelerate or decelerate at any moment without that velocity change permanently modifying the trajectory in ways that can be very difficult to correct subsequently. What there is a gravitational field of extraordinary complexity that acts on the spacecraft at all times, and the ability of mission engineers to read that field and exploit its geometry to propel spacecraft toward their destinations with the minimum possible amount of fuel is one of the most sophisticated forms of engineering thinking that human civilization has developed. The next time you see an image of the solar system and think about the trajectory a spacecraft would follow from Earth to Mars, do not draw a straight line between the 2 points. Draw an ellipse that curves elegantly through space between the orbits of the 2 planets that arrives at the point in Mars's orbit exactly when Mars is there, and that exploits every gram of fuel with an efficiency that would have been impossible to calculate before Newton formulated his laws of motion and gravitation. Because that curved trajectory, that apparent detour that seems to go in the wrong direction for part of its journey, is the answer that physics has given to the question of how to get as far as possible with as little as possible. And in that answer is contained all the elegance and all the depth of human thinking about motion in the universe.